So before I begin, do any of the students in the audience have any questions about the topics we've covered in the past couple of weeks? If not, let me start. So so here's where we were. We have seen so far that neural networks are universal approximators. We must train them to approximate any function, and these are trained to minimize a total error on a training set, which we do through empirical risk minimization. We also saw that we use variance of gradient descent to do this optimization, where gradients are computed through backpropagation. We also saw that vanilla gradient descent may be too slow or unstable because what is a stable learning rate for one direction can be unstable for the other. What is stable for every direction can be too slow. Better convergence can be obtained through second-order methods that normalize the variation across dimensions. Adaptive or decaying learning rates can improve convergence. We saw that methods like rprop that decouple the dimensions can improve convergence, and momentum methods which emphasize directions of steady improvement and de-emphasize unstable directions can also result in better convergence. So moving on, today we're going to look at the topic of incremental updates. We're going to revisit trend algorithms and generalization. We're going to look at some and then going ahead, we're going to look at some tricks of the trade, divergences, activations, and normalization. So although those we will probably not get to today. So let's look at incremental updates. Now, here's where we tried to train the network. There was some hypothetical function shown by this dotted blue line, which we wanted the network to learn. We didn't actually have the entire function. Instead, we had a set of training instances consisting of input-output pairs, and we trained the network to compute the correct output at these inputs, to basically fit the output at each of these training inputs. And the hope was that in doing so, the entire function would be properly estimated. So the overall method was roughly like this. Here the dotted line is the function that you're trying to learn. If you set up the network with some setting for the weights, it's going to represent some other function, like this dotted red line. And so this function is going to be off from the target function. In this particular case, it's below the target function at the first 2 points. It's above the target function at the next 2 points, and below the target function at the final point. Our updates attempt to minimize the total error, the total length of all of these error lines across all training points. And so what gradient descent will do, we'll try to minimize the error at every training point, which means it's going to the updates are going to simultaneously try to increase the function at these locations, decrease the function value at this location, and increase the function value at this location. And this is because the error that we are computing is the cumulative error over all training points, which means that you want the error to be decreased at every single training point, ideally. So after one update, you might have a function of this kind, which is still below the target at these 2 locations and out here, and above the target at these 2 locations. So your next update is going to try to push the function up at wherever we have the green line, and push the function down wherever we have the red arrow. And that will give us a new update. And then repeating the same process, we're going to have a new update, and so on, till we get as close as we possibly can to the target function. But then this is what we are calling a batch update. The problem with this conventional gradient descent is that we are simultaneously trying to adjust the function at all training points, which means we must process all of the training points before making a single adjustment. We want to find the total error across all training points. which means every one of them must be processed. That will give us the total error, and that is what we're going to try to minimize. So this is what we call a batch update. You look at the entire collection of training points before making an update. So here's a poll before we continue. Let me time it.
Says the post cannot be found.
Ten seconds, folks. Okay, does anybody want to answer this question? Which are the true statements here? Somebody want to answer this? Shikhar, which are the true statements? Is anyone online? Can you hear me? Yes. So, are you able to see the poll? Yes or no?
Yes,
Okay.
bro.
All right. Can somebody give me the answer? What are the answers here? I'll wait for an answer. Someone. 2 and 4. Okay. So let's check. All are right, right? The actual loss function we try to minimize requires batch updates. Batch updates minimize the total loss over the entire training data, and batch updates optimize the actual loss function and require processing the entire training data before we perform a single update. So all of these statements were true. Now, this is obviously a problem because you have to process all of the training points before you make a single update, which is not the best thing to be doing. Instead, we can try to do something else. We can try to adjust the function one training point at a time. So the way to think about it is, let's say you're trying to mold something, mold up some putty into some shape. One way to do it is to have develop thousands of arms and to mold the entire shape of the putty at every point all at once, and just try to get the whole thing into shape. But what you're more likely to do is to mold the putty one point at a time. And the problem is that when you push the putty down at one point, it's going to pop up somewhere else. So we have to be careful about this. But nonetheless, you can adjust the function one point at a time, and to make sure that pushing the putty down at one point doesn't make it pop a whole lot at some other point, you're going to keep these adjustments small. So that's what we will do. You might first try to adjust the training function at this point. It's going to push it up over here. If that's going to have an effect at other places, but if this adjustment is small enough, what happens at other locations is going to be relatively minor. Then we randomly pick up some other point, and then we push the function up there, correct the function up there. And then maybe we pick up this point, and here the function is above the target function. We push it down here. And then we pick up another point and correct the function there. And so as we incrementally pick individual training points and make our corrections, keeping the adjustments small at each time, eventually when we have processed all the training points, we would have adjusted the entire function with possibly greater overall adjustment than we would have if we made a single batch update. So is this logic making sense to you guys? I'd like to see some hands raised, thumbs up, something. Is this logic making sense? Right. So, okay. All right. Now, raise your hands. I can actually count raised hands. Otherwise, as opposed to the thumbs up, but let me continue for now. So here's what the incremental update is going to do. You're given a collection of training points. You would initialize all of your weights, and then you're going to go through all the training points. And for each training point, you're going to compute the derivative of the divergence with respect to the parameters of the network and go and update the network parameters at once as soon as the training point is updated, is processed. And so you're going to make your updates instantly. The iterations can make multiple passes over the training data. So a single pass over the entire training data is what we will call an epoch. An epoch over a training set of T samples results in T updates of parameters. Now, so here's what it is. One pass over the entire training data is going to be one epoch. But after a single update occurs after a single instance of the training data is processed. So each update occurs immediately after a single instance is processed. One pass over the entire training data is a single epoch, and the overall training is going to have multiple epochs of training, where eventually these updates are continued until the loss is converged. But then, what are the potential problems with doing this? Does someone want to take a guess at a possible problem? Anyone? I'll wait. Or maybe I can ask. So James, can you lead up? Can you tell me of a potential problem?
No, I'm not sure.
The loss might not converge. Why not?
Because of outliers.
Someone else? Any other issue? Each epoch is going to take as long, just as long as it were if you were doing batch processing. Might be too biased toward the most recent training point. Indeed so. Anything else? So might be unstable. Outliers. Okay, outliers is not. Yes, outliers are an issue, but we won't consider it. Learning rate, overfitting the training. All of these are valid points, right? But let's start with some of the issues. Weight updates will fluctuate rapidly. All of these are valid points. Very true, right? And let me look at one issue that none of you mentioned. So let's say these are my training points. I have these 8 training points. Now, your function, your network architecture restricts the kinds of curves that it can learn. So let's just hypothetically assume that the curve is restricted to being the slightly paraboloid shape. Now, if I go through the training points left to right, when I process all 4 of these training points, I would have minimized the error at all 4 of these, but that is going to increase the error at these 4. Next, I process these 4 data points. That's going to push the curve down here to minimize the error out here, but then the error here has gone up. And so as I keep going back and forth through the data, each time I process these points, this is going to get fixed like so, but the error will go up here. Then when I go to the next set, this is going to go down, but the error is going to go up here. So it can get cyclic. Is this making sense?
Wait, can you explain?
Raise hand if it is, right?
Can you explain why there's like cyclic behavior?
Only 4 of you guys.
Again.
So what did we miss? What did I miss? One of you who didn't raise your hands, what did I miss? Why is this not making sense? Peter.
Wait, sorry.
Okay.
Can you repeat what you're saying? Can you repeat what
There
you're
has to
saying?
be some
Sorry.
reason why only 4 of you have raised hands or training. Wait, is the audio not coming through? The audio must be coming through, right?
Can you hear us
So-
talking you now?
I see. I will see. The headphones are on. Somebody say something.
We are
Testing,
saying something to testing at the moment.
I'm sorry. Please put it in chat. For some reason, the audio over on this thing is not coming to my say something?
Hello.
Now I can hear you. Okay. So, all right. So here we go, right? So how would you fix this? Anyone? Shuffle the training data, right? So what you really want to do is randomize the order. You have to go through them randomly to get more convergent behavior. So you might want to pick something over here, you did push it down here, but the next time you adjust something on the other side. And so if you randomly pick your training samples, then you're not going through the data in the same order and you're not going to get cyclic behavior. And so if you see how that affects your pseudocode, within each epoch, the first thing I have to do is to randomly permute my training samples. And this ensures that I am not processing the data in the same order every time, and that I won't get cyclic behavior. So the story so far, in any gradient descent optimization problem, presenting training instances incrementally can be more effective than presenting them all at once, provided the training instances are in random order. This is what is called stochastic gradient. And this is for any gradient descent optimization for any function, and holds obviously for training neural networks. So my claim over here is that doing this, where we sort of incrementally adjust the function at one point at each time with a small enough adjustment, can actually be more effective than when I process my entire training data and then make an update. That these incremental updates can actually be more effective. So let's see why I make this claim. First, why does the process of incremental updates? So if you don't, you're not shuffling the validation data, you're shuffling only the training data. The validation data have no relevance to this. They are not used to train the model, right? So why does this process of incremental updates work? Under what conditions? And under what conditions? So for the why, I'm first going to start with a very simplistic explanation, which is often given. And I'm going to look at an extreme example. Let's say, typically when you are making an update, you are computing the average derivative. You're computing the derivative of your loss with respect to your parameter, which is the average of the derivatives of the divergences of the network for all the training instances with respect to the parameter. So basically, the gradient that you compute is the average of the gradients of the divergences for the individual training instances. And so each training instance is going to have a different error, right? So the gradient is going to be different for each training instance. So if you had a whole bunch of training instances, their gradients might be all of these little green curves, green lines. And the actual gradient you're going to use is the average of all of these guys, which would be this red line. The final gradient points in the net direction of the average of the individual gradients. Now, consider a situation, this rather extreme situation, where all of my training instances are exactly at the same place. Will they have different gradients? Will their divergences have different gradients? Or will they all be identical? Anyone? They're going to be identical, right? So in this case, if basically all of them have the same divergence, the average divergence is going to be the same as the divergence for an individual instance. And that's all it is, right? And now you can see what happens. Suppose I wait to compute the average gradient over the entire training set and then make an update, as opposed to making an update after just seeing the first training point. Are these two updates going to be different if I have the same learning rate? Anyone? So this update is going to be made with the average derivative. This first update is going to be made with the derivative for the gradient for the first instance. But because all the instances are identical, the updates are going to be identical, which means that if I make an update after each training instance in a single pass over the training data, this function is going to get adjusted a whole lot more than if I waited to process all of my training data for a single update. In other words, this stochastic gradient descent method, which makes an update. And why is this called stochastic gradient descent? Again, just to make this clear, the stochastic gradient descent has to do with the fact that you're randomly selecting your training points at each time. And it's still gradient descent, but it's an incremental update scheme. And if you performed SGD, stochastic gradient descent, in this setting, after processing T training instances, I'm going to get T times as many updates as I would if I were using batch descent. So you can see why SGD can actually result in much greater updates than batch descent. So it can actually adjust your function much faster. Now, if this doesn't have to be the case, right? The training points are very unlikely to be all identical, but what if they are clumped and all very close? Does that logic also kind of hold? Yes, no? Okay, so when is it least likely to hold? When is it least likely to hold? When the data points are kind of diverse and spread apart. So as the data gets increasingly diverse, the benefits of incremental updates decrease. But the point is that the distribution of your data are rarely completely random. For any particular class of data, your distribution is going to have some structure. It's never white, it's never uniform, which means you will always get some benefit from this incremental update paradigm. And this is almost always going to be faster, going to give you better updates than if you just have, than if you first process all of your training data before making each update. So this can be more effective. Now that's kind of a high level explanation. But what considerations must we take and how well does it work? Now, this is going back to the comment that one of you made earlier. Except in the case of a perfect fit, even an optimal overall fit is going to look incorrect to individual instances. So for example, if I've got all of these training instances and I'm trying to fit a line, the optimal line is going to be this red line. Now, is this red line correct for any one of my training points? Is it correct for any one of my training points here? No, it's correct. It's wrong for every one of them, right? So what will happen if I perform an incremental update? Here's what will happen. I'm going to have maybe something like this. So these are my training points. And maybe at some point I have trained this line. Let's say I begin with even a well-trained perfect line. Then I process this instance. When I process this instance, the line is going to swing around and become something like this. Then maybe I process this instance. This line is going to swing around and get closer to this point. Then maybe I process this instance. Then this line is going to swing around and maybe become something like this. Then I process this instance and the line is going to swing around and become something like that. So as I keep processing the data incrementally, the line I'm going to learn is never going to stop correcting itself, because even the best line always has an error, and you're going to have some error for the next or one of the next training instances that you consider. So the training is never really going to converge. Does that make sense? Can you see why this would never converge? So can you suggest a remedy? How would you remedy this? I'm not sure if somebody's saying something. I think maybe not. Decreasing the learning rate, right? So what you would do is something like this. You're going to, so over here, you might, so this problem happens because you're swinging and trying to minimize the error for the latest training point, and the correction you're making is just as strong every single time. So you actually, this can be, to account for this, you want to sort of shrink the learning rates with iterations to make sure that eventually you stop chasing the latest training point hard, and so that the whole thing can converge. And eventually the learning rate is going to become sufficiently minuscule that it will not modify the function that you've learned so far, and you'll get the proper answer. So the way this would modify your gradient descent pseudocode is that this, you still have the same thing. You're going to randomly permute your training instances within each epoch. Then after, you're going to go through your training instances. After each training instance, you would compute the derivatives of the divergence for that instance with respect to all the network parameters. And each network parameter is now going to be updated using a gradient descent rule. But this learning rate is now going to be a function of the iteration. And this thing must shrink with iterations. And that will give us a, that is more likely to give us a better behaving converging algorithm. But then, are there any restrictions you can think of on this learning rate? Anyone? What are the restrictions? I don't expect you to know the answer, but can anybody take a guess? Must be small enough. Yes, indeed. Greater than equal to 0. Okay, so here is the thing, right? So let's say I have let's say this is my optimal function parameter, correct? And let's say this is my initial estimate. So yes, Kevin. Then what at each point, let's say my derivative has an upper bound, and the derivative's upper bound is some u, okay? Which means that whatever your learning rate is, let me call that L, the maximum update is going to be L times u, because u is the upper bound on the derivative, right? Now, for the ith, it's for the these learning rates must shrink. So let's just assume that the derivative is a constant just for argument. I'm looking at the upper bound on the derivative. So I might have an initial learning rate which takes me to here. The next learning rate, I shrink it, takes me to here. The third one takes me to here. The fourth one takes me to here. The fifth one takes me to here. What will happen is that I'm going to, as I chase the latest training point, I'm going to overshoot. I do not want the learning rate, this to overshoot. So I want the learning rates to shrink and shrink fast enough that I'm not likely to overshoot. But then here's the other thing. Suppose I shrink it and I keep shrinking it and I shrink it too fast. Will I ever get here? Am I ever likely to get here if my learning rate shrinks too fast? No, right? So in other words, I want the u times the summation over I equals 1 to infinity of my learning rate to be at least equal to the distance to the between the initial point and the optimal point. So is this making sense? Is this making sense, guys? Right. So why can't we scale? What was that statement? It flew by, right? So the question is, why can't we scale the learning rate with respect to the magnitude of the gradient? That's, well, if you scale it with respect to the magnitude of the gradient, it's like having a fixed size step, is it not? Which is ignoring the gradient, they'll be canceling each other out or some variant of that. The point is this, that you want your steps to eventually get to the optimum. What is the largest possible distance to the optimum? Anyone? What is the largest possible distance to the optimum? Would infinity make sense? Yes, no? Your initial estimate can be infinitely off, right? So if the initial estimate is infinitely off, then this means that the summation of the learning rates must be infinity. So this is a requirement for you to have any guarantee that this incremental update rule is going to converge. You want to be able to get to the optimum regardless of how far away you are when you start. On the other hand, you simultaneously want to ensure that the learning rates are shrinking. So the way you would assure that is that you want to say the summation of Li squared is less than infinity. So the sum of the learning rates are always positive. The sum of the learning rate over the infinite sequence must be infinite, but they must be square summable. The sum of the squares must be finite. That way you ensure that they're shrinking fast enough that you're not going to bounce around. So is this making sense? Yes, no. Just raise your hands. I can count raise hands. Okay. I'll go with 15. Now, so we want it to be we want the squared value of the learning rate to be a convergent series, but the absolute value is not convergent. So we want summation I Li to be infinite to account for the worst case, but at the same time we want summation I Li squared to be finite. So this is making sense. Would learning the rate as we iterate through the training give more example? So it is going to give more if you're going through a sufficient number of. It's not making sense. So what is the question here? What is the problem? Yeah. So why is the square finite? This is the requirement we're having. We want the square to be finite so that we make sure that the thing is that the learning rates are shrinking with iteration. But you want the sum to be infinite to make sure that you're actually able to get to the optimum node regardless of how far it is. Right? Now, what is the sequence of learning rates that satisfies both criteria? What is the fastest sequence of learning rates that satisfies both criteria? Anyone? What will it be? It's going to be between 0 and 1. Well, not necessarily, but yeah. It's a series, right? So I want 1 over n, right? 1 over n is 1 over n summable. It's not. The summation of I 1 over I is infinite. On the other hand, summation I 1 over I squared is finite. So anything that's slower than 1 over n is not going to be infinite. It's not going to satisfy this property. So this is right at the boundary, and this is basically the fastest fastest converging learning rate, which gets you, or this is a learning rate. This is a converging learning rate that is likely to get you to your solution faster. And yeah, and there are other powers, but this one works, right? So typically, what we want is we want the summation of the learning rates to be infinite. If we want it to be square summable. The fastest converging learning rate that satisfies both requirements is 1 over k. And more generally, we are going to have we're going to use something that is roughly equal to 1 over k. For instance, keeping it uniform for some set of iterations and then shrinking it by a factor and keeping it uniform over some set of iterations. Regardless, the actual learning rate schedules that you will use, you will observe satisfy these properties. Now, this first property doesn't necessarily have to be satisfied. Why is that? Anyone? You're not necessarily going to be infinitely far off, right? You just wanted to converge fast enough that you can get to the solution. So the first property in a realistic situation is not very important. The second one is. And if, yeah, k is the iteration number, right? So if the loss is convex, SGD converges to the optimal solution. For non-convex losses, SGD will converge to a local minimum. So let's look at an example of how well this works. This is for, this is not for training a neural network. This is for k-means clustering. And the algorithm has been run many times. The green curve is what you get. The x-axis basically represents iterations. The y-axis measures the total squared error. And the algorithm has been run many times. So the green curve is and the red curve are the average error over many runs, and the bars are the show you the variance. This red curve is what you get using SGD. The green curve is what you get using batch k-means. And what we observe is that SGD converges much faster, but it gives you a much crappier solution than batch. Batch takes much more time. Remember, this x-axis is logarithmic to converge, but it converges to a much lower error, and the variation in the error across runs is also smaller. So while SGD should kind of work for convex problems in a more generic setting, these are the kinds of solutions you're going to get. So SGD by itself is not very satisfactory over here. It will get you an answer, it'll converge to an answer quicker, but that answer is going to be crappier, right? Why does this happen? To understand this, we will look at variances, but first there's a poll. Okay, 10 seconds, guys. Okay. Does anybody want to give me the answer? All correct. Beautiful, right? SGD is an online version of batch update. It can have oscillatory behavior if you don't randomize the order of inputs. It can converge faster than batch updates, but it can arrive at poorer minima. And the convergence to a global optimum can only be guaranteed if steps shrink across iterations, but sum to infinity in the limit. Lovely. Now, so to understand some of this behavior, let's go back and look at how we were modeling functions. To learn a network to model a function, we wanted to minimize the expected divergence. Remember this? This is the actual objective that we wanted to minimize. Right? Yes or no? Raise your hand, because this is. And when I ask you to raise your hand, please do. I will wait for you otherwise, right? Because this is okay. Now, what we did was this. Instead, we computed the average divergence and we minimized the average divergence. Now, our claim is that minimizing the average divergence over the training points is going to some kind of a proxy. So why is that some kind of a proxy? So let's look at so suppose I had many, many runs, right? And it's like each of us, let's say each of us we're training the same model. but each of us chose a random set of training data because each of us has our own restrictions. So we are all given a budget of say 100 training instances. So everyone chose a random set of 100 training instances. Then each of us is going to get possibly a different set of 100 training instances, right? Each of us is going to get a loss. What is the average of the losses that each of us computed going to be? So to consider that, what we are really looking at is the expectation of our loss, right? Which is going to be the expectation of 1 over the set number of training instances times I equals 1 to t loss at the ith training instance, correct? Which is going to be 1 over t summation I equals 1 to t expectation of the loss of xi, and the expectation of the loss is basically expected of the divergence, right? And the expectation of the divergence is the same for any random sample. So this is simply going to be 1 over t times the expected divergence, which is simply the expected divergence of d of x. So what we are saying is that if we ran so if each of us, and if there were a very large number of us, and each of us chose a different set of t training instances, the average of all of our losses is actually going to be the expected divergence. So in other words, the expected value of the loss is the true objective that we are trying to minimize. The expected value of the loss is actually the expected value of the divergence, which is why we claim that minimizing the loss is going to somewhat be a good proxy for the actual objective function that we're trying to minimize. And this is because the expected value of the loss is the actual loss function that we are trying to minimize. Did any of that make sense to you, or was that gobbledygook? Okay, that made sense, right? So, which is why we can use the loss and say this is what we're going to minimize. But then, what we have is that the empirical risk is an unbiased estimate of the expected divergence. But there is no guarantee that minimizing it will, in fact, minimize the expected divergence. We're just using it as a proxy because in expectation, the empirical risk is the actual objective we're trying to minimize. Now, what is the variance of the empirical risk? What do I mean by this? Every one of us chose a different set of t training points. So each of us got a loss. What we know is that the average of all of our losses is going to somewhat look like the actual objective function we wanted to minimize. But the collection of losses all of us got, they're not all the same. So that collection is going to have a variance by itself, right? And what is that variance going to be? And it turns out you can actually compute that variance as well. And it's very simple. If all of us, so we had loss as 1 over n summation I divergence computed at xi, where xi is the training instance. So when I'm adding n, so right here, I can say the variance of the loss is going to be 1 over n squared, the variance of summation I d of xi. So everyone with me over here? Is this making sense? Guys? Okay, Family, what was the issue over here? So, well, I'll assume this does make sense, right? Now, what is each of my training instances is independent. So this d of xi is going to be independent for, is going to be a collection of n independent random variables. What is the sum? What is the variance of the sum of a bunch of independent random variables? What's it going to be?
It's simply the sum of the variances of the
It's
individual
the
numbers.
sum of the variances, right? So this is going to be 1 over n squared times summation variance of the effects, correct? And there are n of these guys. So which is going to be 1 over n squared times n times variance of the divergence. So which is the variance of the divergence divided by n. So what this means is that if each of us just chose one training instance, then it goes without saying that the variance of the losses that all of us compute is basically going to be the variance of the divergence itself, because each of us is just going to compute one single divergence, right? On the other hand, if each of us collected n training points and then computed the average divergence, then the variance across all of our divergences, the divergence, the losses that all of us compute, is going to be 1 over n times the variance of the divergence itself. And it makes sense. If each of us collected infinite training points, each of us is actually going to end up with the actual objective that we want to minimize, and there will be no variance, right? So as the number of training points increases, the variance of the loss is going to be 1 over n times the variance of the divergence of x. So is this making sense so far? Yes, no. Okay. Now, how does it affect us? When I perform SGD with a single sample, right? My training set size is just 1. And so n is going to be 1 over here. N is going to be 1 over here. So the variance of the loss that we get is going to be simply the variance of the divergence itself. And so the sample divergence is an unbiased estimate of the expected divergence. And the variance is also going to be the variance of the expected, the variance of the divergence. Now, if you compare this to batch updates, if I had a batch of n instances, then the variance of our losses is going to be the variance of the divergence divided by n. Whereas if each of us chose just only one sample, the variance of our losses is going to be the variance of the divergence itself. So which means that when you're performing SGD, where you're picking up only one training sample at a time, the variance of your loss is going to be n times the variance of the loss when you actually have a full batch. Now, the math may not make a lot of sense. So let's look at it from pictures, right? This over here, the blue curve is the curve that you're trying to model with your network. The red curve is the curve that the network is currently modeling. And then suppose I picked a batch of n samples, right? So over here, 1, 2, 3, 4, 5, 6 samples. If I pick these 6 samples, then I'm going to learn that if I were doing a batch update, I would learn that I must increase the function at these 2 points. I must decrease the function at these 3 points and increase the function at this point. But then suppose I chose a different set of 6 training instances, and I got these 6 training instances. Then what am I learning? Is there anywhere that I'm actually going to decrease the function if these are my training instances? Is there? No, right? Because every single training instance says you must increase the red curve. And so you're never going to actually decrease it anywhere. On the other hand, if these were my training instances, what would we be doing? We're going to be trying to decrease the function everywhere, right? So clearly, if I'm only choosing 6 points, the specific set of 6 points that I choose is going to affect how I learn my function, right? How do I fix this? What is the only solution? Anyone? Choose a lot more data, right? The more data I get, the more I'm going to represent the error everywhere, and having more samples means that across different sets, I'm still going to get more or less the same set of corrections. But then here's what happens with only one sample. If during SGD, you're picking up one sample at a time and making your correction, right? So your first sample might be there. It's going to say, oh, both functions are fine. I don't need to make any changes. Then your sample might be here, in which case it's going to say, I've got to push up the red curve a whole lot. It could be here. It's going to say, I've got to push down the red curve a whole lot. And so, because you're picking only one sample, depending on where this sample lands, how we are going to correct your function is going to be wildly different, which is why when we perform SGD and you're always making a correction based on only one sample, there is so much variation across runs because you're randomizing your input, and the variance of the loss computed using just one sample is humongous. Whereas over here, you're performing a batch update on a whole lot of samples, and so the variance is going to be much smaller. So here we have this thing, right? Doing batch updates is much slower, but then the variance is smaller and I get a lower error. Doing SGD is much faster, but then it comes to a crappier solution and the variance is much larger. So can one come up with some kind of a compromise? Can you suggest a compromise? So Kevin is kind of right? So SGD uses the gradient from only one sample, so it's high variance, but also provides significantly quicker updates. What is the median? Here's what I can do. I can pick up some subset of samples at a time, a random subset of samples at a time. And so when I pick up a random subset, maybe the first time I pick these three samples, it's going to say, push it up here and push it down there. And that would be my adjusted function. The next time I pick up a different random subset, and it could be maybe these three guys, and it's going to say, push the function up everywhere. And I get a new adjustment. And so I pick up what are called mini batches of these samples at a time. And this is going to give me something better than that stochastic gradient descent, but maybe not as good as mini batch updates. And so, well, the point is batch is very, very slow, right? So you want to keep the batches as small as possible. SGD gives you the fastest number of updates, one per sample, but it has high variance, which is why you want to do these mini batches. You do not, again, ideally, look at this. You want to randomly sample. You want all the other properties hold. These mini batches must be random, right? Which means across epochs, you still want to shuffle your data. And then you select random samples. Because you're randomly shuffling your data, you can actually sequentially select your mini batches, and it's still going to be random because the data is shuffled. But across epochs, you still want to shuffle your data. Now we're going to actually operate on mini batches and update your parameters after each mini batch. Now, how does the mini batch thing work? Again, so look at this. If you look at the expected value of a mini batch loss, using the same logic as before, if your mini batch is of size B, then the expected value of the mini batch loss is also the expected divergence. So in expectation, a mini batch loss is the objective function you want to minimize. But this was also true for SGD, so that's not the big win. The mini batch loss is an unbiased estimate of the expected loss, which means, of the expected divergence of the, which is the true objective function. On average, it's going to be the true objective function. But then the variance is going to be the variance of the divergence itself divided by B. And so to answer your question, again, here's what we had, right? So if this is my batch size, if this is my mini batch size, and if this is my full batch N, right? Then for a mini batch size of 1, the variance of your loss is going to be the variance of the divergence itself, right? Then how does the mini batch variance fall off with mini batch size? How does it fall off? We just went through this. How does it fall? 1 over b, right? It's because the mini batch is size b. And so it's going to fall like that. And as you will observe, 1 over b falls very, very rapidly. By the time you have a mini batch of 100, this 1 over b is 0.01. So even if your batch is like 1 trillion, this is going to be 10 raised to, minus 9 or 10 raised to minus 12, maybe over here. This is 1. But then the gap between 0.01 and 10 raised to minus 12 is essentially nothing. This gap is huge. So basically, there is a point where the mini batch size becomes large enough that you're well past the mean of the curve. And the variance of your loss is small enough to not be a considerable factor. And yes, the batch size is small enough that you can actually process your data in mini batches and still get all the advantages of incremental updates as well as the advantage of batch processing. You're going to get both. And so you really want your mini batch size to be somewhere over here, basically as large as you can fit into your hardware. But given that the variance falls off very quickly with mini batch size, you're pretty good with any reasonably sized mini batch size. So how does that work? If you look at this curve over here, the blue dots, the blue curve shows you the results that you get with mini batch updates. And what you observe is that the variance of the mini batch updates is much smaller than SGD, and it's almost comparable with batch updates. On the other hand, the convergence is as fast as SGD, and so mini batch actually ends up giving you about the same final optimum as batch updates, but at the same speed as SGD. This making sense? Fantastic story. Raise your hands if it does. Right. So, and which is why we use mini batch. Now, convergence is generally defined in terms of overall training loss, not sample or batch loss, and it's infeasible to actually measure the overall training loss after each iteration. So, in these plots, I plotted the loss. I didn't, whoever plotted it plotted the loss, but the loss is computed on the entire training set just to give us an idea of how these things work. But the problem is, if you actually want to compute the loss over the entire training set, you're going to have to process the entire training set. In which case, what was the point of doing batch updates? So based on your batch loss or mini batch loss or your instance loss, you have to take a guess as to what the loss might have been on the entire training set. But the only convergence, and that's what you have to track. But the only convergence that you're guaranteed is not the convergence of the loss on the individual training instances. You're guaranteed convergence of the loss on the entire training data. That is what these guarantees hold for. It's just that you can't really compute it, so we use proxies. Anyway, in practice, training is usually performed using mini batches, and the mini batch size is generally set to the largest that your hardware will support without compromising overall compute time. Larger mini batches imply less variance. Larger mini batches also, however, mean fewer updates per epoch, because as your mini batch size increases, the number of updates you will make per epoch are also going to be fewer. So you get that trade-off. The convergence depends on the learning rate. And the simple technique, you want the learning rate to still satisfy the two properties that we just saw. But simple techniques are like fixing the learning rate till the error plateaus and reducing it by a fixed factor and so on. And this does satisfy the properties we saw. And then you have the adaptive updates, so the learning rate itself is determined as part of the estimation. So here's your third poll. And yes, you're going to get 50 seconds from it. 10 seconds, guys. Okay. Does anybody want to guess the answers? What are the answers? Two is false. All but two, right? You're right. So the story so far is that SGD, for SGD, in the case of SGD, presenting training instances one at a time can be more effective than full batch training, provided they are in random order. For SGD to converge, the learning rate must shrink sufficiently rapidly with iterations. Otherwise, the learning will continuously change. Yes, mini batches are also online, right? The learning rate will continuously change the learning latest sample. SGD estimates can have greater variance than batch estimates. Mini batch updates operate on batches of instances at a time. Estimates have lower variance than SGD, and the convergence is theoretically worse than SGD, but we compensate by being able to process batch processing. Online literally means that as the data come in, which in this case means that every time you read a small amount of data, you process them at once without waiting to read the rest of the data. So it's it's online with a pause. You're going to be waiting till you read in and process your mini batch number of instances, and then you're going and then update your parameters, and then you go on and read your next mini batch number of instances and you update your parameters. In any case, you're not waiting. So as you go through the data, the model is getting updated. You're not waiting all the way to the end to update your model. So that's what online would mean in this context. So now finally, revisiting trend algorithms. Remember, when we spoke of momentum, here's what we had. So one of the problems that, before we even get there, one of the problems with incremental updates is that your update directions, the gradients, are going to keep changing all the time, right? Simply because at each point you are chasing the latest instance or the latest mini batch, and this can be a problem. In the case of batch updates, you're always representing the entire batch, so it's a little more consistent. Here you have this additional noise because at any point you're only looking at some of the training data. So this means that the variation and gradients across iterations can be greater. And that means that you're going to have greater need for techniques that will kind of smooth out the variations and gradients. And for this, the momentum methods that we looked at in the last class end up being a lot more important. Now, I have this on the slide. Don't look at the slide. Can anybody remind me how the momentum method works? Can anyone remind me how it worked? The way we did it was we maintained oh wait, why am I muted? Can you hear me?
Yes.
Okay, so we maintained a running average of the divergences, of the gradients over the iterations. And so the running average basically smoothed out variations in directions where the gradient kept changing direction, whereas it sort of emphasized the gradient in directions where it was consistent, and so you got to the solution faster. The alternative the way we said it was we maintain a running average of the gradient, and we always update the parameter with the running average of the gradient. The alternative that we saw was, so this was the momentum update. If this was your previous step, and this was the gradient you computed in the current iteration, Then the final step was going to be this, or this was the negative of the gradient. This was the step that you computed in the current iteration, which is going to be eta times the negative of the gradient, right? Then this guy, you would add to it some scaled version of the previous step, and that is going to give you your current step. And this is going to be the net update. The new estimate would end up over here. Now, we saw that this had this two-step process where at the current location, we computed the gradient-based update, and then we added a correction, which was some scaled version of the previous update. But this has a somewhat uncomfortable behavior in that while the gradient is sort of taking you in the direction of steepest descent, this correction is taking you away from the direction of steepest descent. And it isn't clear that this is the optimal thing to be doing. Is there something better we can do? And that gave us Nesterov's method, where you first extended your step like so, and then took a step in the direction of steepest descent. And that was the update. And it turns out that putting the step in the direction of steepest descent after the extension is more optimal than putting the steepest descent step before the extension. And so this was Nesterov's accelerated gradient method. And this is for convex functions. This is actually known to be more optimal than gradient descent, momentum. So I think the PyTorch momentum is option 1, and you have to ask for Nesterov or anything wrong, right? So this is Nesterov's accelerated gradient. From the current position, you take a step, which is a beta times the previous step. So that is this guy. You compute the gradient at this location, and this gradient is added to this extended step, which is beta times WK minus 1, and that gives you your final step. So this guy is this red arrow. This guy is the loss computed at the current step plus the red arrow. And this gradient is the gradient of the loss computed over here. The net update is going to be this extension plus the steepest descent step over here. That's your final update. And I saw this showed you this in the last class, that the regular momentum would be taking these blue steps. This is from Hinton, this picture. From this location, the regular momentum would be taking you here, whereas Nesterov would get you much faster to the optimum, right? So so everybody with me so far, did all of this make sense? Because it gets a little, these examples are anecdotal, but there's mathematical proof that yes, Nesterov's method as momentum is superior to simple gradient descent for convex functions, and Nesterov's method is superior to momentum. I'm not getting into the mathematical proofs, but the proofs exist. For non-convex functions, things are more complex. There are no proofs. You can, for optimality, you can come up with some assumptions, and under some assumptions, some things can be shown. But for convex functions, the momentum is better than gradient descent, and Nesterov is better than momentum, right? In either case, what happens is momentum is kind of smoothing out the variations to result in smoother and faster convergence. But then, so is Nesterov. The only difference between what we showed here and what we showed in the last class is this gradient, whether it's momentum or Nesterov, that's going to be computed on the as single instance or on the mini batch, depending on whether it's LGD or mini batch. Now, momentum and Nesterov improve convergence by normalizing the mean of the derivatives, right? So suppose I give you something of this kind. Suppose I give you two functions, two learning groups, And in one case, or two functions, in one case, the gradients are like so, right? Actually, let me draw this slightly differently. So in one case, my gradients are like so. In the other case, my gradients are like so. Can I get the bread? Right? Will the momentum method give me different steps for these two cases? Yes? The positives and negatives are canceling themselves out in both cases. So will the momentums give me the same steps in both cases? Right? But does it make sense? Or should we be saying that in the second case, there's a whole lot more swinging in the vertical axis, and so maybe we should be trusting the vertical axis less? Does that make sense? Right, so they cancel, but the fact that they cancel doesn't change the fact that there is a lot more movement, useless movement in the vertical direction out here than there is over here. So here, even though things cancel, I really shouldn't be paying that much attention to the vertical direction, whereas here, that's less important. So how do I capture the fact that the vertical movement is greater in the second case and account for it in the learning rate? How would you suggest it? Anyone? Multi, yes, it is, but then absolute is a good answer, right? I could be considering absolute average is going to cancel things out. So here's what, if I just sum the derivatives, I'm getting a mean, right? But then the mean is only giving me the average, but it's not giving me any idea of the total movement. I also want to quantify the total movement. If I say that if I find the total movement is too large, I want to reduce the learning rate in this dimension. If the total movement is small, I want to reduce it less, right? And the total movement can be obtained as the sum of the absolute values of the divergences, or is there something similar that gives us maybe a nicer property? Anyone? The root mean squared value, right? The RMS. And so this is basically what we will do, right? Here, and I'm going to sort of skip these steps. What we will do is RMS. So RMS prop actually considers this total movement of this kind. And the way we do it is this. So here I'm going to use a little bit of notation. When I write partial squared d, it doesn't mean it's the second derivative. It means it's the square of the partial derivative, right? And so here's what we do. We maintain a running average of the square of the derivative. That's the RMS value. The RMS value is the average, the mean squared value is the average of the squares of the derivative. But instead of computing an average, we will maintain a running average. This is no different from just computing an average, right? And so I'm going to maintain a running average of the square of the derivative. And then the learning rate is going to be scaled down by the root mean squared derivative, which is the square root of the running average of the square of the derivative. So I'm scaling down the learning rate in directions where I have much wilder swing. And if the root mean squared value is small, if there isn't a lot of wild swinging, then I'm going to scale it down less, or maybe even scale it up. So is this making sense? Is this update making sense, guys? I'm only saying I'd like to see a few more hands because you're going to be using this, right? So this is a variation on, thank you, Peter. Lovely, right? So consider that my derivative is constant. Then when the derivative is constant, what happens to this term? Like if I have a constant slope, what happens to this term? This guy and the denominator are going to be the same. They would cancel out, correct? And the step size is constant. So it's basically going to be dependent only on the sign of the derivative and no longer dependent on the absolute value of the derivative, right? And so this is like R prop, which only looks at the sign of the derivative, but not at the actual value of the derivative. And so RMS, that's why this is called RMS prop. It's like R prop. This is your standard gradient descent rule, except that the learning rate is actually scaled down by the root mean squared value. So this is RMS prop. It's very popular, commented, but can we update this further? What is not happening over here? Anyone? What is it that's not happening here? Think back to momentum. What's it that's not happening? The learning rate is being scaled, but you're using the actual value of the derivative itself, right? So the running average for the derivative, you're not using, this is still your standard gradient descent. The only thing that's happening is that the learning rate is being scaled by the RMS value to account for swinging. So you can take one step further and say, not only am I going to use the RMS value, scale down the learning rate by the RMS value, I'm also going to use the running average for the derivative. And that gives you Adam. It's a combination of momentum with the RMS correction for the learning rate. And so that gives you this one. You maintain a running average of the derivative. That's MK. You would maintain a running average of the squared derivative. That's VK. And then there's a strange MK over 1 minus delta raised to K. What is this delta raised to K? The reason you need delta raised to K is that when you're doing something, if you didn't have this 1 over delta raised to K, then typically what will happen is that you're going to initialize your updates, this running average by 0. And if you're initializing your running average by 0, then for very typically the delta values are very close to 1. So this term is never going to show up. And for the longest time, your derivative is going to remain 0. So in order to account for that, you have this 1 over delta raised to K, which makes sure that this actually gives you something that has significant updates as the iterations progress. And just ensures that the delta and gamma terms do not dominate in early iterations. That's kind of a heuristic hack. But the key idea is this, that you're maintaining both the running average and normalizing the learning rate with the root mean squared value. So there are many other variants of the same theme, like add a grad, add a delta, add a max, but all of them kind of work on the same idea that if you maintain a running average, you're going to sort of cancel out these variations. And if you have some kind of a normalizing factor which looks at the magnitude of the variations, you're also going to account for instability in the gradient. And so that between the two of these, it's going to give you a much more well-behaved, much more convergent update as you get towards the optimum. So generally, there's no explicit learning rate to optimize, but there are, because the learning rate is automatically being adjusted by this RMS value. So you no longer have to have a learning schedule. The normalizing factor takes care of it all on its own. And typical parameters are given here. So RMS drop, you have the beta is 0.001, gamma tends to be 0.9. For Adam, you have delta is 0.9, gamma is 0.99. The delta is the rate with which the mean is updated. The running average of the mean is updated, and gamma is the rate at which the running average of the squared value is updated. So here's a poll. Okay, 5 seconds, guys.
Cannot find the poll.
Cannot find the poll. Can you see it on the slide?
The slide number is wrong. It should be 533.
Oh, I'm sorry. Okay, I'll give you 10 seconds more. We're running out of time. All right, let's just go with this. Can somebody give me the answers? 1 is false. 1 is the only one that's false, right? The rest of the long-term momentum methods consider the long-term average of derivatives. RMS prop only considers the second moment of derivatives, but not the average trend. Adam considers both the average and the second moment, and trend-based optimizers are important to smooth out the variance of SGD or mini batch updates. So here are some nice examples from Alex Radford, which show how these things work. And you can actually look at these plots for and see and relate them to the behavior of these techniques. So this is for Beal's function. The minimum is out here. The initial y guy is out here, and observe, that's SGD, that's the red dot. While everybody else has done, this guy is still, kind of taking this time, right? And momentum, for instance, is wandering off somewhere, but eventually gets there, whereas Adam and his brothers get there really quickly. Nesterov is, in this particular case, it wanders off less, but eventually gets there. But Nesterov actually gets there faster than other methods. So observe that how it is sort of speeding down the direction of the gradient initially, and then it finds that it's beginning to bounce around here, and because it's bouncing, it quickly corrects itself and heads towards the optimum, and actually gets there faster. The Adam type techniques, they don't have the swinging behavior of momentum or Nesterov, but they're much, much faster than SGD, so they actually get there. Now, this one's a more interesting one. This is a long valley, right? So it's basically rolling off out here. The minimum is somewhere down here. Observe how SGD sort of finally finds this place and it's happy. It's not going to move out of there in this valley. Momentum is going to, because the derivative in this direction is very small out here, initially it's going to just keep swinging back and forth. And then eventually when it gets here, it's going to find this derivative and it's going to accelerate. Nesterov does the same thing, but much quicker. So Nesterov gets there much faster. Whereas something like Adam is not going to really get affected by the derivative in this direction, and it's going to head directly but smoothly towards the minimum. And RMS prop in particular, beyond a point, the slope is constant. And so you can see that although RMS prop heads in the right direction, it becomes, it does so in a very sedate and slow fashion, whereas the rest of the techniques, everything except SGD, simply blow past it, right? And this behavior can be predicted from the function shape itself. Here's another one. Here the minimum is out here. And once again, you can see how SGD basically finds the minimum and kind of stays there. Momentum and Nesterov follow the derivative, but then eventually find the right one and get to the correct solution. Whereas Adam and co, they head there directly. And here is the interesting thing. If you wait long enough and the optimum is far enough, in every one of these examples, you're going to find that Nesterov actually gets there faster than anything else. Even here, right? So The story so far, gradient descent can be sped up by incremental updates. Convergence is guaranteed under most conditions. The learning rate must shrink with time for convergence. SGD, you update after each observation and can be much faster than batch learning. Mini batch updates, you update after mini batches. This can be more efficient than SGD. And convergence can be improved using smooth updates, RMS prop, and more advanced techniques. So I'll stop right here, bang on the dot. I'll stay online for a few questions. And otherwise, thank you for being on Zoom.
Thank you.
Thank you.
Thanks, Professor.